Good day, everyone. I'm Wang from the University of Amsterdam. The focus of our presentation today is towards automating federated learning operations at scale by leveraging common workflow language. This work has been done together with Kuronis and Zhiming. Federated learning is a revolutionary method that allows for collaborative model training across multiple decentralized devices while maintaining data privacy. And it can effectively handle decentralized data without raw data exchange to train a joint model by aggregating and distributing local training. It is a key solution for scenarios where data cannot be centralized due to data privacy or regulatory concerns. It involves various AI models, data, and heterogeneous infrastructures that store the data. Development operations, or DevOps, is a set of practices that combines software development and IT operations, aims to short the development lifecycle and provide a continuous delivery with high software quality. MLOps is an extension of DevOps principles to the field of machine learning. MLOps focuses on automating and streamlining the machine learning lifecycle. It includes model development, training, deployment, monitoring, and retraining. FLOps is a relatively new term that extends the concepts of DevOps and MLOps to federated learning environment. FLOps focuses on managing the complexity of federated learning pipelines within the lifecycle, such as federated learning design, federated learning training, and federated learning operations, ICT opens related to federated learning training. And such as coordinating distributed training processes, ensuring data privacy, and maintaining model quality across decentralized data sources. In the federated learning research and development, we usually have to consider its diversity and customization, whatever what kind of federated learning research works you are conducting in the ecosystem. For example, decentralized data stored in heterogeneous infrastructures, researchers might train diverse federated learning tasks, such as content-based medical image retrieval, classifiers, artifact detection, with decentralized data. Moreover, federated learning has diverse aggregation strategies that usually perform as different typology. Not only centralized, but also decentralized or hierarchical federated learning typology. So we observed that reconfiguring and automating such diverse federated learning scenarios are still challenging. On the other hand, and in terms of automation, we have introduced DevOps, MLOps, and recent FLOps for automate software development, machine learning development, and federated learning development processes, respectively. However, only very few research works could support diverse federated learning configurations. What we want to achieve is not only supporting federated learning diversity or scalability, but also high automation for diverse federated learning scenarios. So, how do we achieve a highly automated federated learning process while supporting diverse federated learning scenarios? This is the main research question we are going to answer in this work. To address this, we introduced CWL FLOps. By leveraging CWL in FLOps, and CWL integrates into the federated learning scenarios by encapsulating the logic for data distribution, model updating, and aggregation strategies. Then we can automate the federated learning operations at scale. We have investigated workflow patterns CWL supported patterns and FL descriptions with different scenarios, including but not limited to centralized, decentralized, hierarchical, or synchronous federated learning topology. This abstraction simplifies operation, making it more accessible and manageable. For example, we have abstracted centralized and decentralized federated learning descriptions in CWL, and here is an example of decentralized federated learning description. The architecture of CWL FLOps has been published in a poster in eScience conference last year. We concluded 4 key features of CWL FLOps, and it can support customizable FL services by reusing the source code and reconfigure them as federated learning building blocks through GitHub repositories and Docker Hub. And in terms of the composable FL topology, and it enables users to design and compose their own federated learning workflows in CWL. To support scalable FL clients, we developed a communication REST API. It can discover FL client nodes and make clients registered to initialize a federated learning setup. Also, with GitHub action workflows and Terraform configuration, we can achieve full automation for the federated learning development, deployment, execution, and logging with GitHub action. The project source code in terms of decentralized federated learning scenario has been published at GitHub repository. Welcome to check and test. And to evaluate the proposed MERST, we conducted several experiments. In the setup, we used the federated learning source code from GitHub and employed an AWS cloud infrastructure to mimic the scalability or the scalable federated learning nodes with decentralized datasets, and that has been partitioned from the MINST dataset. We also considered running CWL workflows locally or on remote cloud virtual machines. And we collected the execution time for comparisons with between Python-based federated learning and CWL-based federated learning implementation for deployment and execution. We tested the CWL scalability with 2 clients and 10 clients in the AWS cloud. In the centralized CWL federated learning, we can say it has successfully collected the execution time cost. And with the data size increase, the time cost will also increase. Similarly, we collect the decentralized CWL FL execution time with the same data sizes. It also has been successfully deployed and executed in with the CWL workflow and cloud infrastructure. We also investigated the CWL overhead compared to the pure Python-based FL implementation, in which we use job lab, parameter, and requests to achieve the automation of deployment and execution. As you can see, in the 2-client scenario, the CWL workflow decentralized scenario, the difference between the Python-based and the CWL-based implementation, the average overhead, the average time overhead is around 0.19, 90 minutes. And if we increase the client number, as you can see, the average CW overhead it is about 0.20 minutes compared to Python-based FL implementation. It's still very small. In the centralized federated learning scenario with CWL and Python-based implementation, you can see in the two clients, CWL overhead is around 0.18 minutes. In the 10 clients scenario, we can see the CWL overhead is still around 0.19 minutes. So the average CWL overhead is relatively stable and very small and very low. So the cost, the time overhead of using CWL implementation can be ignored. To sum up, we have seen the transformative potential of CWL in automating federated learning operations, and we conclude the following main advantages. It is customizable, it is composable, and it is scalable. And it can also support full automation with GitHub Action. Besides, the CWL overhead compared to the pure Python-based implementation, it is relatively stable and low overhead, which means it is almost 10 or 12 seconds. And in the future, we will investigate more relative work. For example, we want to investigate the model quality control within the federated learning scenario of federated learning lifecycle management with CWL plus a decentralized virtual research environment. Thanks for your attention and time, and I'm looking forward to see how each of us can contribute to this evolving landscape.